Section: Introduction. In this section, we discuss the impressive abilities of large language models, LLMs, in reasoning tasks, such as mathematics and coding, with examples like ChatGPT, Claude, and Gemini. The release of GPT-4 has heightened interest in LLMs that excel in reasoning and the methods that support this capability. A key feature we value in these models is their ability to identify and correct mistakes in their own responses, a process known as self-correction. When an external reward model is available, research shows that LLMs can improve their responses based on this feedback and decide when to stop correcting themselves. This has been effective for both mathematical reasoning and general tasks. However, without external feedback, LLMs face challenges in refining their responses based solely on their internal capabilities, which we refer to as intrinsic self-correction. While traditional reward models are trained with additional components for various tasks, recent studies suggest that LLMs can generate their own reward signals. For instance, the LLM as a judge method prompts the model to assess its outputs, acting as a substitute for human feedback. Another approach involves generative reward models that treat evaluation tasks as instruction following problems, using the likelihood of generating specific outputs as the reward. Building on these ideas, we explore self-rewarding reasoning models that combine three functions within a single LLM: generating detailed reasoning steps, evaluating the accuracy of its responses, and revising previous answers based on self-generated rewards. Our main contributions include: 1. Self-rewarding reasoning framework. We present a framework that merges the generation and evaluation processes into one LLM, allowing for independent reasoning, assessment, and correction. This integration simplifies decision-making and reduces computational demands compared to using external rewards. 2. Algorithmic framework for self-correction. We propose a two-stage self-correction process for mathematical reasoning that relies solely on data generated by the model itself. In the first stage, we use sequential rejection sampling to create long reasoning paths that capture self-rewarding and self-correction behaviors. Fine-tuning on these paths helps the model identify and correct its errors. In the second stage, we enhance these patterns through reinforcement learning with rule-based signals. 3. Empirical validation and analysis. Our extensive experiments demonstrate that self-rewarding correction significantly outperforms intrinsic self-correction. We also conduct studies to understand the learning dynamics of our framework, providing insights into its effectiveness. The training codes and datasets are available on GitHub. In the related work section, we review studies that connect to our project. Our work aligns with research on self-rewarding alignment, where we unify generation and evaluation in a single LLM. While other methods focus on self-improvement during training, we emphasize using an external reward model for learning signals. Our study targets inference time alignment for reasoning-focused LLMs, using self-rewarding signals solely for guiding inference. We also relate our work to self-correction in LLMs, noting that previous studies have shown that LLMs struggle to self-correct without external rewards. Our approach aims to enable LLMs to evaluate and correct their responses independently. We introduce a self-rewarding reasoning framework that allows a single LLM to effectively detect errors and self-correct. Compared to existing methods, our framework equips models with self-rewarding capabilities, allowing them to optimize computational resources by selectively revising initial attempts. We will design experiments to illustrate this concept, and our approach differs from others by using sequential rejection sampling to create fine-tuning data, followed by reinforcement learning to enhance these behaviors. Section Summary. In this section, we discuss the development of a self-rewarding reasoning framework for large language models, LLMs, that integrates generation, evaluation, and correction capabilities into a single model, thereby simplifying decision-making and reducing computational costs. We also outline our two-stage self-correction algorithm that enhances mathematical reasoning through self-generated data and reinforcement learning, demonstrating its effectiveness over traditional intrinsic self-correction methods. Section: Rule-based RL for LLMs mathematical reasoning. In this section, we discuss rule-based reinforcement learning, RL, for enhancing mathematical reasoning in large language models, LLMs. We note that rule-based RL gained popularity after the success of DeepSeek R1, prompting open-source projects to replicate its results using Qwen models. These approaches focus on two main scores: the correctness score, which checks if the final answer is right, and the format score, which ensures the answer follows a specific format. This differs from earlier methods that relied on neural network-based reward models. We observed that self-correction tends to occur during RL training, which we refer to as an AHA moment. However, our initial experiments and open-source replications with Qwen-2.5 math indicate that while base models show some self-correction ability, it is limited. Additionally, we found that standard rule-based RL does not consistently improve self-correction without further design. Interestingly, we did not see similar improvements in models like Llama, even when using the same algorithms and data. We believe that Qwen-2.5 math and DeepSeek R1 benefit from extensive pre-training on high-quality mathematical data, which may include self-correction patterns. Since these datasets are not publicly available, we cannot confirm the specifics. In contrast, our research demonstrates that a warm-up stage using a carefully curated dataset allows models to learn self-correction patterns more effectively. This foundation supports rule-based RL in enhancing these behaviors consistently. We also note that our two-stage framework and most experiments were conducted before DeepSeek R1 was released. Next, we define the self-rewarding reasoning process as a multi-turn Markov decision process, MDP. After receiving an initial prompt, the LLM generates a reasoning attempt and evaluates its response. If the model deems its answer correct, the process stops. Otherwise, it refines its response and evaluation until it reaches a correct self-assessment. We assume access to a ground truth verifier that determines the correctness of responses, and we utilize the Torah verification script for this purpose. We adopt a two-stage training framework, starting with self-rewarding instruction following fine-tuning. We begin with an initial LLM and collect demonstration data through a sequential rejection sampling process to improve the model's reasoning abilities. We then refine this model using RL to enhance its ability to assess correctness and improve previous responses. For self-rewarding instruction following fine-tuning, we train LLMs to evaluate reasoning steps as an instruction following task. We allow models to include reasoning in their evaluations and require them to output specific tokens indicating their evaluation results. We tested various token options, such as asking if the final answer is correct and using explicit markers like verify, correct, or verify, wrong. Our findings show no significant performance differences among these options. In our data collection process, we generate initial reasoning responses from datasets and sample self-evaluations, retaining only those that match the ground truth. We categorize these evaluations into correct and incorrect groups. For incorrect responses, we sample completions to gather trajectories that successfully revise them. We also collect correct-to-correct trajectories to understand how models respond to incorrect judgments. Ultimately, we filter the dataset to keep specific types of data for fine-tuning. We limit our data collection to 2 iterations due to resource constraints and retain only 1 trajectory per base sample to manage dataset size. We then fine-tune the LLMs using a standard pipeline, although we noticed that multitask training can sometimes lead to stability issues and slightly impact initial performance. To address this, we also train on correct attempts for samples in the correct category. Section Summary. In this section, we explore rule-based reinforcement learning, RL, for large language models, LLMs, in mathematical reasoning, highlighting that while self-correction can emerge during training, it is not consistently enhanced without additional design. We propose a 2-stage training framework that combines self-rewarding instruction following fine-tuning with RL optimization to improve the model's ability to evaluate and refine their responses effectively. Section. KL regularized reinforcement learning. In this section, we aim to improve our self-rewarding IFT models through reinforcement learning. We explore both deep reinforcement learning methods and direct alignment algorithms. To support this stage, we assume there is a reward function for each trajectory, which we denote as U* for the trajectory consisting of states and actions. Instead of deriving a proxy reward from data, like in previous models, we focus on the oracle reward, which indicates whether the final result is correct. This approach helps reduce the risk of reward hacking and is known as rule-based reinforcement learning. We will also investigate additional rule designs for assigning reward values or ranking data. Following standard reinforcement learning from human feedback methods, we optimize a KL regularized objective. We can define optimal value functions and policies for a KL regularized Markov decision process with a set time horizon and deterministic observations. One benefit of our approach is that it allows for deterministic external messages during state updates, which will be useful in our simplified research framework. We utilize direct preference optimization to solve our equations, particularly using the multi-turn DPO framework, which accommodates deterministic observations. To streamline direct preference learning and avoid explicit reward training, we implement a trajectory-level preference structure. Specifically, we assess the likelihood of one trajectory being preferred over another using the sigmoid function. For our evaluation, we test the model's mathematical reasoning abilities using established benchmarks like Math 500, Olympiad Bench, and Minerva Math. These datasets are of moderate size and cover various mathematical topics. For training, we primarily use prompts from the Numia MathCot dataset, dividing it into subsets for different stages of our process. During inference, our model generates up to 4,096 tokens, with the LLM 0.5.4 version speeding up the process. We employ two types of metrics to assess our models, one for mathematical reasoning and self-correction, and another for reward model accuracy. We consider various metrics, such as the accuracy of the first attempt, final accuracy, and improvements in accuracy from the first attempt to the final answer. We also measure the accuracy of our reward model and the likelihood of modifying correct answers to incorrect ones when faced with misleading rewards. For our experiments, we use the Qwen-2.5 Math 7b base model, which has been pre-trained on extensive mathematical data. We collect a dataset of 32,000 trajectories through sequential rejection sampling, balancing correct and incorrect attempts. During fine-tuning, we pack samples into blocks and set specific training parameters. In our reinforcement learning setup, we adopt iterative DPO training with defined learning rates and batch sizes. We collect responses for prompts and extract comparison pairs based on correctness scores. A validation set is used for model selection, focusing on accuracy at the second turn. We also consider baseline methods to enhance self-correction abilities, including training free approaches and fine-tuning. We evaluate intrinsic self-correction and methods inspired by expert iteration in reinforcement learning. For single-turn reasoning, we explore various baselines that do not involve self-correction, including iterative DPO and PPO methods. We ensure a fair comparison by using the same number of training samples across different approaches. Section Summary. In this section, we enhance self-rewarding IFT models through reinforcement learning by utilizing an oracle reward function to reduce reward hacking risks, and we implement KL regularized objectives alongside direct preference optimization, DPO, for efficient training. We evaluate our model's mathematical reasoning abilities using standard benchmarks and various metrics, while also comparing our approach against several baseline methods to improve self-correction and single-turn reasoning capabilities. Section: Main Results. In this section, we present our main results in a table, noting that there may be a rounding error of 0.1. We find that intrinsic self-correction with prompting generally does not work well. Specifically, we observe that when models attempt self-correction without explicit rewards, their final test accuracy often decreases. Our analysis shows that models frequently change their initial answers, regardless of whether they were correct, because they lack a clear way to decide when to refine their answers or stop correcting. Even when provided with accurate rewards, models using only prompting show only slight improvements in transitioning from incorrect to correct answers. For instance, on the Math 500 benchmark, prompting with accurate rewards results in just a 1.4% improvement in these transitions. We also note that the star-raft method, which fine-tunes models based on revised incorrect attempts, does not significantly enhance performance. It raises the incorrect to correct transition rate from 1.4% to 5.0% on Math 500 but still experiences a 6.2% rate of correct to incorrect transitions. Furthermore, the star-raft plus variant, which includes correct to correct transitions, becomes more cautious in altering initial responses. While this reduces incorrect corrections, it also lowers the rate of incorrect to correct transitions, ultimately harming test accuracy. These findings are consistent with previous research and underscore the limitations of intrinsic self-correction, even with training. In contrast, self-rewarding reasoning models significantly outperform existing self-correction baselines. Across all tasks, these models consistently achieve higher final accuracy and better transition rates compared to baseline methods. We find that fine-tuning on synthetic trajectories that encourage self-correction leads to models that are much better at correcting their own errors. Unlike star-raft, models trained with self-rewarding IFT show significantly lower rates of correct to incorrect transitions, indicating they are more adept at recognizing when to stop correcting due to the added self-reward signals. For example, on Math 500, self-rewarding IFT achieves a 5.0% transition rate from incorrect to correct, compared to 1.4% for intrinsic self-correction, and a 0.4% rate for correct to incorrect, compared to 15.4% for intrinsic self-correction and 3.8% for star-raft plus. We also compare self-rewarding reasoning models with reinforcement learning training against single-turn models. Both PPO and DPO self-rewarding models achieve higher final test accuracy due to the additional correction step. For instance, the self-rewarding IFT combined with PPO reaches a final accuracy of 43.4% on Olympiad Bench and 38.4% on Minerva Math, compared to 39.5% and 33.1% for the single-turn models. Similarly, with DPO, self-rewarding reasoning models achieve 78.6% on Math 500, 40.1% on Olympiad Bench, and 34.6% on Minerva Math, while single-turn DPO models score 76.8%, 39.0%, and 31.6%, respectively. However, self-rewarding models require more tokens during inference due to the extra correction step. To ensure a fair comparison, we will also examine the behavior of self-rewarding correction under different test time compute budgets in a later section. Lastly, we find that the deep reinforcement learning algorithm outperforms direct alignment algorithms. Specifically, PPO shows a significant advantage over iterative DPO. For example, the PPO-trained model achieves 43.4% final accuracy on Olympiad Bench, while the DPO method reaches only 40.1%. This suggests that when absolute reward signals are available, enforcing a preference structure may not be necessary and could even hinder performance. Another reason for DPO's lower accuracy may be its limited data utilization. We can only collect comparison pairs for 40% to 60% of prompts, while the rest either yield no correct trajectories or all correct ones. Consequently, DPO uses less training data than PPO, which may contribute to its reduced accuracy. Section Summary. In this section, we report that intrinsic self-correction methods generally reduce test accuracy due to models' inability to discern when to refine answers, while self-rewarding reasoning models significantly outperform these methods by achieving higher accuracy and better managing incorrect to correct transitions. Our findings indicate that self-rewarding models, particularly when fine-tuned with self-correction behavior, effectively improve performance and reduce incorrect transitions compared to traditional approaches. Section. Reward Model, accuracy. In this section, we evaluate the accuracy of our reward model within our self-rewarding framework, which integrates both the generator and the reward model. We find that the Qwen-2.5 Math-7B base sometimes fails to adhere to the required format, either skipping the self-evaluation step or not presenting the evaluation results correctly. This occurs in less than 10% of cases, so we concentrate on those samples that include the evaluation step and involve human oversight to summarize the findings. Our results, shown in the table, indicate that the self-rewarding IFT model excels at identifying correct trajectories, achieving an accuracy above 90%, even with a balanced training set. This contributes to the small differences we observe in the main table. We also note that reinforcement learning, RL, training, including both PPO and DPO methods, does not always enhance reward modeling accuracy. Analyzing PPO checkpoints reveals a trade-off between correctly and incorrectly classifying responses. The PPO training explores this trade-off to maximize overall accuracy, a pattern we also see in DPO training. Notably, the best PPO model tends to focus on correctly identifying trajectories, which may lead to lower accuracy in spotting incorrect responses. This aligns with the observed lower differences in classifications, as correcting an incorrect answer is typically more difficult than maintaining a correct one. We will explore how data composition affects reward modeling accuracy in the next section. Regarding the learning dynamics during the RL stage, we find that while RL training boosts final accuracy, this is influenced by both the initial accuracy and the differences between turns. We see that improvements in final accuracy mainly stem from higher initial accuracy, although this comes with a reduced reliance on self-correction. Our plots show that early in the RL training, both initial and final accuracies rise, with a stable gap between them. However, around the 100th training step, the increase in final accuracy is primarily due to better initial accuracy, indicating less dependence on self-correction. We also track the average length of generated responses. Initially, the length decreases as the Qwen-2.5 Math-7B base model generates lengthy Python code, which can lead to incomplete reasoning. This is discouraged by the reward signal. Later, the length increases, suggesting that reflection and self-correction are being encouraged by RL training. Ultimately, the length decreases again, coinciding with higher initial accuracy and smaller differences, indicating that models are learning to provide correct answers on the first attempt, while self-correction is being discouraged. This is further supported by the reward model accuracy, where RL-trained models tend to be more conservative in their evaluations. In the next part, we continue to explore the self-rewarding reasoning framework using a simplified two-turn conversation format. Previously, we combined multiple reasoning steps into a single long trajectory, which posed challenges, especially for the Qwen-2.5 Math-7B base model, as it often struggled to follow instructions for evaluating or revising responses. To tackle this, we implement a two-turn framework where the user gives clear instructions between steps. After the model generates its reasoning and self-evaluation, the user provides specific instructions based on the evaluation. This approach allows us to directly determine the self-rewarding signal from the ground truth oracle reward, facilitating controlled experimentation. While this simplification may lower reward modeling accuracy, it enables us to modify the self-rewarding signal more easily. Section Summary. In this section, we evaluate the accuracy of our self-rewarding framework, noting that while the Qwen-2.5 Math-7B base model occasionally fails to follow instructions, it generally achieves over 90% accuracy in recognizing correct trajectories. We also introduce a simplified two-turn conversation framework to improve the model's self-evaluation and correction process, which allows for more controlled experimentation despite potentially reducing reward modeling accuracy. Section: Base Model, Task, and Datasets. In this section, we describe our base model, tasks, and datasets. We utilize Qwen-2.5 Math-7B base as a robust model pre-trained on a large set of mathematical data. To broaden our evaluation, We also experiment with the Llama model series, specifically Llama-3 to 8B and Llama-3 SFT, the latter of which is fine-tuned on OpenMath Instruct 2 to 1M. Although both Llama models are generally less capable than Qwen-2.5 Math 7B base, Llama-3 SFT performs better than Llama-3 to 8B. We assess the mathematical reasoning abilities of these models using the Math and GSM-8K benchmarks, which suit their strengths. For Math, we train with 7,500 problems during the self-rewarding IFT stage and use an additional 7,500 prompts from OpenMath Instruct 2 for MDPO training, applying a similar approach for GSM-8K. We select models based on a validation set of 1,000 from OpenMath Instruct 2. Since we treat the task as a multi-turn chat, we can directly apply Axolotl's training code. During inference, the model generates up to 2,048 tokens per round, with LLM 0.5.4 speeding up the process. For the Llama SFT training setup, we use a learning rate of 2 millionths and a batch size of 32 for Llama models and 64 for Llama-3 SFT. We train outcome-supervised reward models using standard SFT methods and datasets, with full hyperparameter details available in our GitHub repository. We notice that models sometimes fail to follow instructions for self-rewarding corrections, but this happens in less than 5% of cases. In such instances, we stop after the first round and take that output as the final answer. Our experiments with Llama models show trends similar to those with Qwen models. We find that intrinsic self-correction, whether with or without specific training methods, does not consistently fix errors in self-generated responses. Models often change their initial answers regardless of their correctness, making these methods more useful for weaker models, like Llama-3 to 8B on the math task. However, for stronger models, such as Llama-3 SFT on the GSM-8K task, these methods can actually lower accuracy on the second attempt. In contrast, self-rewarding IFT models consistently enhance accuracy on the first attempt by correcting errors while keeping correct responses intact, showcasing the effectiveness of our framework. To further test the self-rewarding IFT model, we adjust the self-rewarding signal to match the oracle reward, allowing us to evaluate the model's correction abilities without the influence of reward quality. For instance, the baseline Llama-3 SFT shows an improvement of 8.8% in correction capabilities, while models fine-tuned with self-rewarding IFT show a higher improvement of 9.7%. We also find that self-correction requires generating multiple responses, so we compare models under the same inference budgets. Previous self-correction methods often do not outperform self-consistency when limited to the same number of responses. To tackle this, we analyze self-rewarding correction under scaled test time compute budgets by sampling multiple reasoning paths and using majority voting for the final output. Our results indicate that, with a fixed inference budget, the self-rewarding correction model consistently surpasses independent sampling methods. For example, independent sampling achieves 40.4% accuracy on math with 64 samples, while our self-rewarding correction method achieves 42.8% accuracy with only about 26.4 samples. A key reason for this efficiency is that our models do not always generate 2 samples per trajectory. They stop early when confident in their first response. For instance, using Llama-3 to 8B, we generate an average of 1.65 samples per trajectory for math and 1.25 for GSM-8K, resulting in significant computational savings. Section Summary. In this section, we evaluate various models, including Qwen-2.5 Math 7B base and Llama models, on their mathematical reasoning abilities using the Math and GSM-8K benchmarks, finding that self-rewarding IFT models improve accuracy while reducing computational costs compared to traditional self-correction methods. Our results indicate that while intrinsic self-correction methods struggle with stronger models, our approach effectively enhances performance by generating fewer, more accurate responses. Section: Ablation Study on Data Distribution. In this section, we conduct an ablation study on data distribution. We find that self-rewarding IFT models outperform self-correction methods that use external ORMs. To explore the dynamics of the self-rewarding signal, we compare self-rewarding IFT models with an external ORM trained on the same dataset, as shown in our results table. We notice that self-rewarding IFT models achieve better performance in both turn-to accuracy and the change in accuracy over time compared to self-correction with external ORMs. This suggests that combining the generator and reward model into a single large language model, LLM, could be beneficial. However, we also see a significant difference in reward model accuracy between the external ORM, which evaluates the Llama-3 SFT policy, and the self-rewarding ERM used for the self-rewarding IFT policy. Specifically, the self-rewarding IFT method achieves a 70% accuracy in identifying correct trajectories, slightly better than the 66.9% accuracy of the Llama-3 SFT policy with the external ORM. On the other hand, for incorrect trajectories, the self-rewarding IFT model has a 76.4% accuracy, which is much lower than the 88.4% accuracy of the Llama-3 SFT policy with the external ORM. To understand this difference, we use the self-rewarding ERM to assist in the self-correction of the Llama-3 SFT policy. Interestingly, in this scenario, the reward model accuracy for Llama-3 SFT aligns more closely with that of the external ORM, indicating an out-of-distribution issue. This occurs because the policy shifts from Llama-3 SFT to self-rewarding IFT during the self-rewarding IFT stage, while the reward model is trained on data from the original Llama-3 SFT policy. Additionally, when we evaluate the same Llama-3 SFT policy with both the self-rewarding ERM and the external ORM, we find that self-rewarding training slightly reduces the reward model's effectiveness, likely due to model capacity limitations. We believe that addressing the out-of-distribution issue and utilizing a larger base model could improve the performance of self-rewarding models, which we plan to explore in future work. We also examine how data composition in self-rewarding IFT affects ORM accuracy. In our experiments with the Qwen and Llama models, even though we use a balanced training set with equal numbers of trajectories for incorrect and correct first answers, the reward modeling accuracy remains unbalanced across the two classes. The Qwen model excels at recognizing correct trajectories, while the Llama model is better at identifying incorrect ones. To analyze this further, we perform an ablation study on dataset composition using the Llama-3 to 8B IT model, testing three variations: a balanced training set, a set with more incorrect trajectories, and a set with more correct trajectories. We also look into the effect of adding correct to correct trajectories. Our findings indicate that, with a fixed number of incorrect trajectories, increasing the proportion of correct trajectories biases the ORM towards predicting answers as correct. This leads to higher accuracy for recognizing correct trajectories but lower accuracy for identifying incorrect ones. Specifically, as we shift from a balanced training set to one with more correct trajectories, the accuracy changes from 72.1% and 75.3% to 63.6% and 82.4%. This highlights a trade-off between the accuracies of the two classes, as changes in the reward model's accuracy directly affect the transitions between correct and incorrect answers. When comparing results with and without the additional correct to correct trajectories, we find that these additional trajectories mainly lower the probability of changing a correct answer to incorrect when faced with misleading rewards. This suggests that the models become more cautious when adjusting initial responses, which makes sense since correcting an incorrect answer is typically more difficult than maintaining a correct one. Section Summary. In this section, we demonstrate that self-rewarding IFT models outperform self-correction with external ORMs, achieving higher accuracy in recognizing correct trajectories, although they struggle with incorrect ones due to an out-of-distribution issue. Our ablation study on data distribution reveals a trade-off in reward model accuracy based on dataset composition, indicating that increasing correct trajectories enhances the recognition of correct answers but diminishes the identification of incorrect ones. Section: The impact of distillation. In this section, we examine the effects of distillation. While we primarily focus on policy training, where we train our models using only self-generated data, we also utilize the Llama-3 to 70B model to generate a specific output in the self-rewarding IFT of Llama-3 to 8B, as shown in our results table. We find that data from the teacher model significantly improves the accuracy of the first response, which in turn enhances the accuracy of the second response. However, a stronger output does not improve the model's ability to self-correct, indicating that their self-correction capabilities remain similar. Additionally, off-policy training leads to a notable shift in the data distribution, which reduces the accuracy of the reward model. Therefore, we conclude that distillation is more effective for enhancing first response accuracy, while self-generated data is better for developing self-rewarding reasoning models when a teacher model is available. Next, we explore additional rule designs in reinforcement learning training. We conduct preliminary experiments on reward assignment strategies for PPO training and data ranking strategies for DPO training to assess their effects on model performance. For a fixed input and first response, we test several ranking strategies. We categorize the last two types of data based on reward signal comparisons and exclude ambiguous comparisons. For simplicity, we only train the model for one iteration and present our findings in a table. Across different base models and tasks, we observe that MDPO training with one specific ranking strategy effectively reduces the probability of misclassifying a correct initial answer as incorrect. As a result, models fine-tuned with MDPO show a significant decrease in their correction rate. Interestingly, even though the generation of the first response is not directly involved in training, the ability to correct in the second response transfers naturally, leading to improved first response accuracy. However, we also notice that if the probability of misclassification becomes too low, it can make the models overly cautious, which ultimately reduces their correction rate. This is confirmed in experiments using one specific ranking strategy, where the correction rate decreases. Conversely, training with another ranking strategy encourages models to adjust their initial responses, resulting in a higher probability of misclassification and a slight improvement in correction ability. We find that while one model trained with this strategy shows a lower correction rate, this is mainly due to lower reward model accuracy and higher first response accuracy. When we compare the ratio of corrected responses, our self-rewarding IFT achieves a certain percentage, while the MDPO-aligned model slightly surpasses it. Moreover, combining both ranking strategies often yields optimal results, helping models better recognize when to adjust their initial responses. Section Summary. In this section, we explore the effects of distillation and various ranking strategies on model performance, finding that while distillation enhances turn 1 accuracy, self-generated data is more effective for self-rewarding reasoning when a teacher model is available. Our experiments with MDPO training reveal that specific ranking strategies can significantly improve model conservativeness and correction abilities, leading to better overall accuracy in multi-turn tasks. Section. DPO training cannot consistently improve the reward model accuracy. In this section, we find that DPO training does not consistently enhance the accuracy of the reward model. During our experiments, we notice that MDPO training alters the generation distribution of the first answer, which affects the reward model's accuracy in unpredictable ways. For instance, when we use only the first dataset from MDPO, we see a decline in recognizing correct answers on the math task. However, when we combine this dataset with a second one, we improve the recognition of correct answers but reduce accuracy for other categories by 10%. Despite our efforts to fine-tune the data combination in the third dataset, we still experience a drop in recognizing correct answers. Additionally, with a balanced dataset in GSM-8K, the accuracy for two classes worsens. Overall, we do not achieve consistent improvements in reward model accuracy. We suspect this inconsistency arises from a mismatch between the DPO implicit reward and the sampling probability. Exploring algorithms like SIMPO, which optimize the sampling probability directly, seems promising for future research. We also examine different reward signal designs in PPO training to enhance self-correction, especially in the later stages. We test two approaches. If the first attempt is wrong but the final answer is correct, we assign a reward of 1.5. Otherwise, we give 1.0 for a correct final answer and 0.0 for an incorrect one. We split the learning into two stages. In the first stage, we focus solely on correctness-based rewards. Then, we initialize the model from this stage and apply the modified reward system. We notice that models can exploit the first reward design by intentionally giving a wrong answer initially and correcting it later. For example, after 150 steps of PPO training, the test accuracy on the first attempts for MATH 500 is only 18.6%, while it jumps to 77.6% for final answers, indicating they are taking advantage of the reward structure. Furthermore, the models struggle with the two-stage learning in the second plan, and we do not see any improvement in test accuracy. While simple reward modifications do not succeed, we believe that more advanced multi-turn reinforcement learning strategies, like SCORE, could enhance RL training. However, implementing multi-turn deep RL training and separating self-rewarding reasoning steps remains a challenge in open-source frameworks, which we plan to explore in the future.